want to leave you with 2 bits of good news. First of all, we live in a very special time. The only time in the history of the universe we can basically verify that we live in a very special time. Again, that's facetious. Because anyone, anytime can be thinking that. The real message I want to give you is, as I told you, you are insignificant, the future is miserable, and the real future is this. In the far future, we will be lonely and ignorant, but dumb. And those of us who live in the United States are completely used to that. Thank you very much. Okay, now let me just warn you, especially those sitting in the middle of the rows who are thinking a lot about liquids, that I won't take many questions in public. I'll be happy to answer questions in private, but I don't want it to drag on forever. So I'll take maybe 4 or 5 questions in public, I think, and so you don't have to worry if you have to go to the bathroom. You'll be done soon. Okay?
All right, well,
is there any, shall I pick? I'll pick. I have complete power, yes. I have a question about, hold on, I can get a couple of microphones.
I have a question on it. If the universe is flat and the constant doesn't equal 1, is there a force that as the universe expands at a increased velocity, that is not going to be destroyed by that action?
No. You're absolutely right to be really confused, right? The universe is expanding. The energy density of empty space is remaining constant. So the total energy of the universe looks like it's increasing. How can that be? Is there some force that's causing, and in fact it is. It turns out empty space, if it has energy, has negative pressure. And what that means is that gravity is doing work on matter and as it's moving it apart. So gravity is literally doing work, and so the energy of the universe depends on the work that's being done on it. So because empty space has negative pressure, the total energy of the universe is actually increasing with time. And it's really weird, but it's perfectly allowed in general relativity. And it's just really weird. That's why you never thought it was the case. But it's the case. Yeah? I think someone's going to get you a microphone.
I was just curious, if the universe is expanding and expansion is accelerating, isn't that the definition of an open universe?
That's a good point. No, in fact, in an open universe, but you did remind me of something I wanted to say, so that's very good. In an open universe, what happens is that the universe is basically approaching a constant velocity. In a flat universe, it's slowing down but never quite stopping. In a closed universe, it stops. In an open universe, it slows down, but it then approaches a constant. It expands at a constant rate. In this kind of universe, it's actually expanding at a faster and faster rate. But, in fact, what I just told you is garbage. Just right now, maybe not everything, but just what I told you right now. And this is what's so neat about all this. I got into cosmology because I wanted to know how the universe is going to end. We now know the universe is flat. We solved that problem. We now know how the universe is going to end, right? Wrong. It turns out geometry is irrelevant. Once you allow empty space to have energy, everything changes. An open universe can collapse. A closed universe can expand forever. It doesn't matter. So all that energy and emphasis we put into trying to learn the geometry of the universe to answer that question was completely irrelevant. My purpose in becoming the scientist that I am today is gone. Okay? There was no purpose in my becoming the scientist I am today or whatever. The point is that it turns out to know the future of the universe, it doesn't matter whether it's open, closed, or flat, even though we know it's flat. We won't know the future until we know the nature of the dark energy. Because we don't know that dark energy won't disappear. We don't know that it's truly the energy of empty space or just some weird thing that mimics the energy of empty space and it's going to go away. So until we know the nature of the dark energy, we can't really predict the future. And it doesn't matter what geometry of the universe is. It's completely irrelevant. In order to answer that question, we need to know the nature of the dark energy. And to know the nature of the dark energy, we have to have a good idea. Because we're probably not going to learn anything more from observations, in my opinion, about the nature of dark energy. We're going to have a theoretical understanding of how it arises, and that means we're going to have a good fundamental theory of particle physics. and gravity, which we don't have yet. And so it could be 10 years, 100 years, 1,000 years before you know the nature of dark energy, and that means we just don't know what the future is going to be. It's irrelevant. All that stuff in books about open, closed, and flat is just irrelevant. So we're going to go in the back with our, well, let's go with the way to the back, and then you can have the last question, which is maybe, or two of you. Both are good questions.
Hello. When you put that graph, that 3D graph on the board,
Yeah.
and it was that distant galaxy cluster, and it showed the distribution of mass.
Yeah.
The dark energy was kind of a very large mass between the spikes, right?
Yeah, there's a huge mass distribution. Most of the center went out near the edge.
Exactly. That's my question, which is, why did it hang around the spikes? Why does dark energy like to be near normal mass?
No, it's the other way around. That's what's great. You're being myopic again. What's great is, no, this is what's neat. The important stuff is the dark matter. This is dark matter, not dark energy. And so the galaxies are just turning it around for the fun of it. Okay, so what happens in the history of the universe is that the first things to collapse are big lumps of dark matter. Then the stuff that's made of you and me wants to fall in the potential wells of where the dark matter is. So that's why the galaxies hang around the dark matter, not the other way around. Because they're the important things, we're just around for the fun of it. Okay? Okay, good. Sorry, too late, because I'm going to promise these two people the last question. So we'll go to you, and then you. And then the last question. Go on.
Do we know if any or many galaxies receding faster than the speed of light and have already disappeared beyond the event horizon?
Yeah, absolutely. In fact, you can work out that if the energy of empty space is what it is, that had we evolved 5 billion years earlier, there are more galaxies we could have seen then than we could see now. So there were already things we missed. We just were too stupid to evolve early enough to see it. And so it's really not just the future. Information is really big. In fact, that's why I've used this. I've gone to Congress, and I said, fund cosmology now while we have a chance. The problem is that 2 billion years is a lot longer than 2 years, which is a long-term future for a Congress person. But it's true. Things have already started to disappear. We're already losing information in principle.
I'm wondering, in the far distant future, when there's only the visitor universe, and all we can see is our own galaxy, which is still expanding faster and faster.
No, our galaxy won't expand. That's the key point. That's the other big misimpression. Not everything expands in the expanding universe. Those things which are gravitationally bound do not expand in the expanding universe. So our galaxy isn't expanding as the universe expands. The solar system isn't expanding. The Earth isn't expanding. You're not expanding. Well, maybe you're expanding. But everything that's gravitationally bound remains at a constant size. So our galaxy won't be expanding. It'll just be sitting there waiting to die. Just like... That's a really good way to expand this galaxy.
Well, ladies and gentlemen, Professor Krauss will be here to sign copies of his books. If you have a copy you'd like to get signed, we also are selling books over there. If you want to purchase a copy, line up over here. If you'd like to get a signed copy, line up right here.
Thank you very much.
The reception, please congregate around Jesse here, who will take you to our booked room. Otherwise, please get a book signed.
I don't know. I realized that